Alright, hello Link341. Today we are going to be talking about Trills. I'm in a different environment, so apologies for that. I'm in a grad's office, and there might be a little bit of background noise. Anyways, we will start with Trills, and this will be a really exciting lesson for everyone, and we will learn a little bit about airplanes as well and physics of the airplane flying. First things first, fun stuff. So I'm going to show you a game which we came across many years ago. Dr. Winters shared this with us. This is the guess the word game, and the guess the word game looks like this. So basically your assignment is to guess the word based on the movement of the tongue, of lips as well, and yeah, basically these two are moving and you have to guess the game. The data that was collected was observed or just collected with the X-ray microbeam method. At some point they said no more X-rays, no more unnecessary X-rays, let's use microbeam X-rays. They placed pellets on people's tongue and palate as well, and on people's lips. So these are the lips on the right hand side, this is the tongue, this is the palate, this is the pharyngeal wall. So let's see what this speaker is saying. We have to guess. Right, it starts a little bit low, it goes up, it touches the alveolar ridge, sort of. The lips are not moving so much, so it can be a dorm. No, because of not so much dorm. Point. I don't see p here. Or yeah, there is a lip like point. Maybe that. Right. Never. I don't know how back of the tongue that would be.
Point.
I'll go with point here because the lips are already in this position of p, and I going down as you say point. Jaw is being open a little bit, and you're touching the alveolar ridge at the end. Point. All right, I made the first one. Let's embarrass myself on the second one. All right, okay. So the tongue is already high up, as if it's saying glowing. No. Cash. About. Cash. Interesting. So I don't think it's about, I don't think it's 10. Glowing might be. The tank is really high. Cash. I'll go with
Glowing.
Obviously the tank is really high up, and there's a lot of alveolum touching by the tank, so glowing 2 times, right? A little bit of alveolar ridge here, so yeah, I'll stop here while I'm still ahead, and you can play around with it. You should also hear or listen to Miriam Makeba's song. It's a click song. Let me play it for you just for a little bit to introduce this wonderful singer who was singing in her own language. And she says at the beginning of in the introductory part that she was singing in her own language, and when they asked her about why are you making that noise, she said, well, that's my language. Let's listen to it.
This next song is also a South African song. It's a Xhosa wedding song.
This is a very cool recording.
Everywhere we go, people often ask me, how do you make that noise? It used to offend me because it isn't a noise, it's my language.
Yeah, so I won't play it because you cannot hear it very well, but I'll send it your way, so no worries about that. So back to aerodynamics. I'll show you what this is later. First of all, we can make stops, right? And to make stops, we start the airflow. Remember the Boyle's law: air flows from high to low air pressure. So your air pressure beneath the glottis needs to be higher in order for it to flow into the vocal tract. When it does, you stop the airflow, you make an airtight seal, and afterwards you release air, or you just release these two articulators, and you're making the release burst. So this is called release burst, and I'll show you how that looks like on on the Bengali example. This Bengali example will show to you that there are regular stops without aspiration and without unreleased diacritic. That's why these two are not necessary. So I will perhaps do this. So pay attention to the recording, and we'll see that there is no need to transcribe these sounds as unreleased and aspirated here, right? Like aspiration, but just like a simple t stop, that's a ordinary voice stop. Here it is. Here it goes. Okay, Bengali view and edit. I think the last one is the best example of it. All right. So this is the waveform up there, and there is just a slight release burst happening there when you're popping off your articulators. So you're holding, you're moving them apart.
Tat, 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 tat.
Right? And this part here is the regular stop, just a stop, a simple stop. There is a maybe slight aspiration here, but it's just noise, insignificant. And no one released because it is released, right?
Tat, tat, tat,
Right? You can hear that
tat.
that, and then a slight release of the air over there. All right, so this is the simplest aerodynamic version, simplest aerodynamic example. Air flows from high to low pressure. There is slight explosion or no explosion at all, depending on the stop, and air pressure difference does the work. I want to introduce you to another aerodynamic method, and here it is. The method that we can think of is what we call a trill. So if I make this sound, and I ask you what kind of sound is this, you'll probably say trill, because you know that the lesson is about trills, right? And it's always fun. This is what we call a voice bilabial trill. So you make it like this, right? And yeah, that's about it. Voiced bilabial trill is sort of an expression of I'm tired, I cannot think about anything, and you say, right? Something like that. Examples here that we have are from Kili and Titan, which are the languages spoken at the island of Manus, north of New Guinea. And here is the bilabial trill with this pre-nasalized portion here, but don't pay attention to it. Try to produce bilabial trill in isolation first, and then when you get a hang of it, you can produce it within a word, which is much more difficult.
Brunkei,
Okay.
Bulim,
Brulin,
Bulei,
brule,
Butukei,
okay. The Titan has less of a trilling than Kili. So when we are making the trill, we are pushing the both lips by pushing the air out. So we are opening and closing the lips by just blowing the air out of our mouth, and the lips are in in this as an obstruction. They are in our direction of the airflow. So as if you're blowing and your lips are bothering you, right? They are in your way. So something like right, like that. It helps if you know blow up a little bit of your mouth, right? So this is how we make those. But the question is a very important question. Yeah, one thing is I want to say as well, that you can first try to make this in isolation and then in a word, because it's much more difficult. So when you say then you just try and continue okay, and so on and so forth. That's how you will manage to do that. These. Titan has a less or fewer number of these cycles that are denoting opening and closing our lips, so that's why it does sound like b, regular b, but it's actually a trill. Okay, how fast? That's a question for you, right? I always ask how fast this happens, and you may want to guess, right? But I would normally invite volunteers to come to the whiteboard or blackboard or whatever, and in front of the class they would record a Bilabial trill. So let's try. I'll try to record it for now, and because of COVID, I would probably not invite you to come to the whiteboard. Let me give it a shot. Okay. All right, that's good. So I think that's good. We have two examples here. Let's see the first example. The first example shows kind of a equidistant pattern here of the spikes. So there is one spike, another one, and here from this spike, I think forwards we have, for example, 1, 2, 3, 4, 5 spikes. Okay, I may take these 5 spikes and try to see how fast was I opening and closing the lips. It seems like was pretty fast. It is 1.17 seconds, and these spikes denote that when the air pressure increases abruptly and then decreases, abruptly decreases, increases, because the air gets out of your mouth. So 0.18, let's say. Okay, not the best number we will work with, but let's say 0.18. Now what we need to do is I will open up a new slide here and try and answer this question how fast, right? So if we have if we have a 0.18 seconds, right? For 0.18 I make 5 of these cycles, right? Now the question that we usually ask in order to have this level level playing field is how fast or how often do these cycles occur in 1 second, 1 full second, right? Okay, how to answer that, right? Well, you can think about 0. I might open the calculator here. Sorry. Okay. It's Apple TV. Calculator. That's what happens when you have so many applications. Calculator. Right. Okay. Right. Good. All right. Here it is. So 0.18, 5 seconds. So plus, oops, so we will do the following: 0.18 plus 0.18. Not good. Obviously I can calculate on foot. 0.32, right? So for 0.32 I make 10 cycles. 5 more, right? Then 0.50, I think so, I make 15, right? Let's see. No, my bad. 36 obviously and 54. Okay, 15. Then 18 more seconds, so that would be 0.72. Hope I'm good using it properly. Let's see, plus 0.18. Yeah, finally. And now we have a 0.90, like 25 seconds, right? And now I don't want to calculate. We may round it up to how many? Like 10 more. So that would be what, 3 cycles, right? So in 1 whole second, 1 second, if I make 10 more, what's this? Second, if I make 10 more, that would be no, 10 more seconds, that would be 30 cycles. So 30 cycles per second, right? That's what I make. And these this frequency is expressed in cycles per second, CPS, right? We call this number of repetitions per second frequency. So this would be frequency, right? And I won't write the whole thing, right? But it's frequency. And now we have to think about period as well. Period. And I'll use the calculator this time. Of course. All right, period. So for period, we calculate the period by using this formula, 1 per frequency, right? So what is the time that one cycle needs, right? How fast does one cycle occur? And that's what we are trying to answer. So 1 per 30. I'll invite the calculator here. Don't want to make another mistake. Okay, 0.0333, right? So it would be 0.033 cycles per 1 second. So not even a whole cycle per 1 second. And it does, and I go by very fast. So my period is that, and this is the frequency. Another unit for frequency is hertz. Look at this. By, I think Humboldt Hertz was the scientist behind this, and they named the whole thing after him. So this is the frequency and this is the period. We're slowly entering into the acoustics realm, or basic acoustics realm, and it will be fun. Okay, again, conserving the energy. It will be fun to explore this. So basically, as I said, I just showed you period and frequency differs, right? Now, do we close and relax our lips each time we do this? So when we for example produce a stop, a regular stop like a but, we close and relax our lips but once, right? But do we close and relax our lips each time we do this? No. Why is that so? Oops. When the air blows lips apart, why they don't stay apart, like ba, and that's it, right? Why aren't they apart? Yeah, so that is the question we have to answer right now. And this guy here will provide an answer to our question. This is the Daniel Bernoulli, who was a famous, or maybe not in his time, but now very popular mathematician. And he lived in the 18th century. he came up with what they called Bernoulli Effect, and which says that in a flowing stream of particles, the pressure exerted by the particles is inversely proportional to their velocity. So pressure equals constant per velocity. Again, similar equation as for Boyle's law, but different principle here, right? We have pressure, which is exerted by some particles, which is inversely proportional to their velocity. What this basically means is that the higher the velocity, the lower the pressure. The lower the velocity, the higher the pressure. So velocity in this case indicates speed of the moving particles. So the higher the speed of the moving particles, the lower the pressure. The lower the speed of the moving particles, the higher the pressure. And that's Bernoulli effect. This effect is known to be valid for, to be used by physicians, by physics major and physics researchers out there in order to explain how airplanes are flying. There are, of course, many more principles to that, but we can explain how air is moving and what air can do to the surrounding with its movement. In the same way, we can explain by using this effect what happens when we are trilling, when we are producing a trill. And the interesting story about Daniel Bernoulli is that he entered a science contest when he was young and tied for the first place with his dad. So his dad entered the same contest, and his dad was so upset that this happened that he disowned his son and never spoke to him again. Those were the good old 18th century days, right? And that's a story we have right now as a kind of anecdote, but let's say it's true. One guy we remember is definitely Daniel Bernoulli. So yeah, the difference, as I said, between this one and the Boyle's law is that we're dealing with a flowing air and not the air that is trapped somewhere. Boyle's law, if you remember, the air flows from the areas of high to low pressure areas, but it is sometimes the air, especially when we produce speech, that is trapped within our vocal tract, right? So here we're dealing with the moving air, and yeah, let me show you how this works, right? I'll draw again. Good old drawing. All right, so imagine you have a wall, right? Imagine you have some kind of particles, molecules of air moving around, right? And exerting some pressure, normal pressure. Nothing is specific is happening. They're just moving, right? They're just that. They are levitating, and they exert a normal atmospheric pressure on these walls. So they're touching the walls, and they're moving, touching the walls and moving back and forth, right? Now, if somebody were to below them, very fast, exert a force of air onto them, something else would happen. So what would happen is that they would squeeze, they would become much faster, right? And they would not extend to the walls anymore because of the velocity of the flowing air. The air is flowing much faster right now, okay? So it's flowing much faster into this direction, and there is no time. There is simply no time for them to exert any pressure upon the walls, right? So there is simply no time. And let me show you how this works. So, for example, I have two papers, right? Two papers here. And there is some air pressure on this paper, a regular one, right? Nothing too fancy, nothing too special. It's an atmospheric pressure. But now, if I do this, right, and below, what do you think will happen? Will the paper go like this? Will they move closer, or will they be brought apart? I don't know what you answered, but let's try it out. They're actually moving closer, counterintuitively probably to what you thought. They're moving closer because, as I said, there is no time for air to make certain pressure to keep them in their initial position. And because of this motion of air, which is very strong now towards the camera, towards the computer, the air is moving much faster, and there is no time simply for them to make this pressure towards the walls of the papers. And that therefore the pressure reduces inside, so the pressure gets lower. P gets lower, low, and here outside, perhaps, P or pressure is increasing. So it gets higher just because the pressure gets low within the walls. And that is how the Bernoulli effect is operating. Basically, higher the velocity, higher the speed, lower the pressure. Lower the velocity, the higher the pressure. And there you have it. As simple as that. Of course, there are so many examples of Bernoulli effect out there in the world. One of the examples is the airplane wings. They operate on Bernoulli effect as well, but a bit differently than some other effects or something else that you might think of, such as a fan with which you dry your hair. So this is what happens. This is a wing. I won't draw. This is a stationary wing or just an airplane wing. It sort of looks like that. Maybe it's not completely like that. And this is the air that is going above the wing. So wing, something like this, is going above the wing and below the wing. So imagine an airplane flying, right? The air is going above and below. The air, because the wing is a little bit leaned towards this left side, the air needs more time. So it needs more time to come to this point, right? To reach this point here. And the air gets faster above the wing. And you know what happens when the air gets faster? Well, the pressure reduces, right? So the pressure is not so big. So maybe if I try and do this, let's see whether it works. So I'm blowing below the paper and nothing happens. But if I blow, let's see, just above the paper, no. Yeah, you can see that this side of the paper went up a little bit just because the below the paper has higher pressure than above if I blow the air out, right? And that happens with airplanes. So air needs more time to get to this point, to get to the point of meeting of the two upper and lower sides. And what happens here is that the air below needs as much time as it it needs normally. So air below exerts the exact same pressure, it remains level, but air above exerts a lower pressure because of higher speed, higher velocity, and that's what keeps air in the air, airplane in the air. If you think about it, it's simple physics. Of course, there are so many mechanisms, more principles than that, and physics professors can tell you that, but this is a simplest way of explaining how the airplane flies and how it gets stuck into the air. I don't have a frisbee here, but Dr. Winters is a frisbee enthusiast, to say the least. He even competed in some frisbee competitions. I didn't know it was a sport at all until I came here to Calgary, which was fun, and he's really good at it. Anyways, a frisbee looks like something like this. Like this is a plate, right? A plastic paper plate, whatever. And these sides of frisbee are there are sides of frisbee like this. That if you throw it, if you throw it like this, the air needs more time to reach the edges of frisbee. And here, the air needs less time to reach the edges, which means that air exerts the same level of pressure, and here the air needs to move much faster, so it exerts a lower pressure, which basically means that we get a frisbee to fly. So I can give this a shot. Let's see if this will work. Okay, so I'll just fly it like this. Okay. Yeah, cannot see it. But if I flew it like this, if I flew it like this, it would drop very fast. It would drop quickly because the pressure here is higher than here, right? And that's what we don't want. So if you are making a paper plane or making a paper frisbee, always fly it or throw it with this bulky side up, right? That's basic physics, right? Another example, another case is the effect of a shower curtain. If you have a loose shower, not the one that is firm, you can get into the shower and turn on some hot water, right? And for some reason, the shower curtain will start creeping up your way, and you wonder what is happening, right? The reason why is the Bernoulli effect. When you turn on the shower, the water will start air moving around, right? And the air movement will increase in the tub or within the tub where you are, right? And this will change the pressure levels between, the inside and the outside. The outside pressure level will be higher because there is no movement, and the inside pressure level will be lower because there is movement. So the shower curtain slowly creeps up your way, which always makes you uncomfortable, and it's always creepy. I already showed you the pieces of paper, how they are working. It's basically the same mechanism with bilabial trills. So you are pushing the air or blowing the air out of your mouth. By contracting your lungs and by doing, applying the Boyle's law in this case, the air gets out of your mouth, and then you just place the lips for being blown out, like, and then you don't have to do anything much. You don't have to move them back, or they don't remain in the open position because the force is making them move towards each other. So there is this pressure difference that is constantly making them open, close, open, close, open, close. So you're exerting some force, you're opening them, and then because of this pressure difference, they are getting close, right? There is more pressure in the atmosphere than within your tract, so they're getting close. Then you push again, and the the lips open, then they get close again, or they move towards each other again, and so on and so forth. And you saw how fast that happens. Like, what was the period? Very fast for me. Once in 0.033 seconds. Yeah. Now, I want to show you an epic trill. Let me just grab it here. No. Okay. I'll minimize this. I have, just bear with me. I'll find it in a second. Everything is open here. Yeah, here it is. So this is Reese Witherspoon. She is a famous actress. She acted in Legally Blonde many years ago, and in Tonight Show, I think. I don't know, something like that. But you probably know of her, about her, and this is the epic trill that she's making. Let's because this is an Instagram video. They didn't do a sound. It's a slow-mo of her trill. So yeah, that goes on for a while, but what's happening here is that she's blowing the air, in this case through her teeth, basically, and the air is under the Bernoulli effect, making her lips open and close so many times that I call this the epic trill. It helps if you do this, blow up a little bit of your cheeks, because that's the air where the air can be stored. You know, it has to go somewhere, and this accumulation of air then goes out. All right. Okay. Yeah, that's fun. Cool. Okay, that was Reese Witherspoon, and we'll continue with our lecture on trills. Is schematized in this trilling schematic. Lips are close, adducted. That's a nice term to learn. So when lips are closed, we say adducted. They're brought together, and I didn't want to use it before right now because it's a technical term, and there is some force, right? Adducting or adductive force that is making the lips being brought together. And this is the outside of your mouth. These are the two lips, and this is the inside of your mouth. Obviously, this is the upper and lower lip, right? Okay, so what's happening here? So the lips are closed, they're brought together. The pressure builds up inside of the mouth from compression of lungs. So you build up the pressure, like, right? There is nowhere to go. Air pressure inside of your mouth increases. Outside air pressure remains constant, right? So we have a constant there. Pressure differential between inside and outside builds up, right? And this exerts force against the lips, which makes the pressure differential blows open lips. So this pressure actually is blowing the lips, and it's making them making your mouth open. Air rushes from high to low areas of pressure. Very clear. The opening of the lips means that this delta P decreases slightly the entire pressure. So when you open the lips, the pressure inside decreases. High velocity of air flowing between lips. There is high velocity right here, right? Between the lips, and air pressure decreases between the lips because of this high velocity, and that's where Bernoulli effect kicks in. Lips, because of that low pressure, they get sucked back together. And of course, back to stage one, If air is flowing out of the lungs, pressure will rise again within the mouth. Process will repeat itself as long as air is pushed up from lungs and lips are held tightly against each other. So we repeat the stage once again. This is what the air should look like. These are the schematized version of the molecules of air in the regular repetitive cycle, which we capture in with our microphones and our ears, of course. What we hear, but yeah, the pressure again builds up, and we repeat the whole thing once again. I hope that was clear, and you can just go back to it to repeat it. There are some other trills, of course, out there, not only bilabial, but they all operate at a similar principle, although the bilabial trill is the most interesting one with respect to Bernoulli effect. This one is interesting because we call it alveolar trill, and it's written with this symbol here, R, because most of the languages in the world use this trill and not the R or that is used in English, right? The upturned R or the retroflex R. And these are again examples from Keeley and Titan. Ruin, Rekein. You can sing along to these. Okay. Yeah, so about this one, what you can do is place your tip of the tongue towards the alveolar ridge. So place it against the alveolar ridge and try to blow through it. So like, and after a while you're going to produce it. Something like, right? As if you're forcing yourself to say, right? You're forcing yourself to exhale and make this many times, because trill has to happen many times, meaning that when you're blowing the air out, the tip of the tongue will move and hit the alveolar ridge 3-4 times, let's say, right? And this is a more common symbol, more common sound in the worlds of the languages, in languages of the world, sorry, than English retroflex, right? You can voice it if you will. That might help as well. So you can say right, vibrating your vocal folds, because you're then exerting more air towards your vocal tract, which will help you produce this trill. Some other places of trills that we know of are uvular trills, and this is the symbol for uvular trill. A uvular trill is I need some water, maybe, yeah, this coffee. Okay. Right? You need to be hydrated a little bit. For this one, if it's not in your inventory, like it's not in mine, this is typical of French language, for example. And yeah, and maybe not poor example, I would say good example is Edith Piaf. Edith Piaf was a singer in the 50s, and this is her famous song, No Regrets. Let's hear it out.
Non, rien de rien. Non, je ne regrette rien.
Yeah, and so on and so forth. You can listen to her, tremendous singer, right? She is producing No Rien de Rien, right? And lots of trills. What you can do with the uvula trill, you can just place your tongue against the uvula or the back of the tongue and try to exert some air or blow out some air from your lungs. So you are making a repetitive motion with your tongue, like right, something like that, and it has a flavor of r. That's why it's written like this as well. Okay, so you know, this is the example of the trills, alveolar and uvular. Are there any other places of articulation for trills? That's an interesting question, because people always, or most of the time, think these are palatal or pharyngeal, but in fact there is a glottal trill. Um, yeah, voicing for these trills occurs when air rushes up from the lungs and the vocal folds are brought together. They are adducted, right? And the voicing in this way occurs. But because the vocal folds are such a light tissue and such a tissue that is not massive, right? They can be brought together, adducted and abducted. They can move apart very many times, many more times than you would do for a bilabial trill, I guess so, right? Yeah, and they're very, very small. If you visit someday cadaver lab, you'll see that they're this big, right? So it's easy to make certain motions when the air is pushed out, and when you exert this pressure, that lowers the pressure of air and then makes them adducted, right? So this is an example of what it looks like. Basically, these spikes here show you the number of time vocal folds open and close, and this is typical for creaky voice. Creaky voice is what we make sometimes when we speak, but this is the intentionally made creaky voice. This is Professor Winters. Yeah, he has creakiness in his voice anyway, so it's not difficult for him to produce it. Maybe I'll try, because I am also known for speaking in a creaky voice sometimes. Okay, let's give it a shot. Let's see how that would work. So I want to close and open the vocal folds many times, but still I want you to be able to hear, to count how many times I produce them, and by that I mean count the number of spikes. Okay. Not the best recording, but okay, there it is. Yeah, as I said, not the best recording. But you can basically calculate the number of spikes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 spikes or 10 closings, openings per 0.2 seconds. So twice as faster than I was going for a bilabial one, right? If we think about that, am I going to calculate again? Perhaps. So 10 per 0.2, 0.4 would be 20, 0.6 would be 30, 0.8 would be 40, and one whole second would be 50, right? So that's how we would calculate this one. This is a fourth of a second, so yeah, oh no, fifth of a second, so 5 times 10, 50 would be the frequency, 50 hertz, right, of my vocal folds vibrating, and the period would be 1 per 50, so 1 vocal fold opening and closing is going on in 0.02 2 seconds. That's low. That's really fast in comparison to bilabial trills, right? However, this is the slowest type of voicing, and this is what we call a creaky voice. The flow of air from the lungs forces the vocal folds to open and close. I already said that. So basically, we go from this mode of voicing, this mode of laryngeal setting. We also call this laryngeal setting because it's about our vocal folds which are in our larynx, and the laryngeal setting in this case is creakiness or creaky voice. Another laryngeal setting is the modal voice. That's a normal voicing, and the rate of glottal trilling is considerably faster. So when you produce in comparison to yeah, you cannot really count the number of times you do this. I mean, it's fairly easy to do this in Pratt, but I won't show you this right now because that's something we will work on. Anyways, I can try and record this and say ah in a normal voice, although my voice is pretty terrible right now. All right, so if I try and calculate this one, that will be much more difficult. So maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0.07 seconds, right? Okay, and this is approximate calculation. So again, okay, zero energy, approximate calculation. So bear with me. So 0.07 seconds. That would be what? 1/10 of a second, even less. So 0.07. See what we get. 0.07 plus maybe times 15. Okay, times 13, something like that. Okay, 14. So it would be 14, right? We can do it like this. So basically, I make 10 cycles per 0.07 seconds, and I make 140 because of 14 plus times 10, right? That would be 14 times 10, 140 in 1 second. That would be my frequency here. And maybe, I'll just say maybe, if I show you this pitch and maybe get pitch, I'll see the same result. Okay, similar results. I was based on the waveform, it's difficult to tell, but around we're in the ballpark, right? 120 hertz, and we will learn about this in very soon. But this is basically how you can do it step by step. Although it's really not really precise, it's much better to do it in Pratt like I just did it with pitch. We'll talk about pitch very soon. Anyways, modal voicing is much faster than creaky voice. That's why we call creaky voice slow type of voicing. Although creaky is much faster, or the openings of vocal folds are much faster for this one than other trills out there, right? Because of the setup of the vocal folds, and because of the structure of the vocal folds, which is very small. How fast do you think the vocal folds open and close in normal voicing? I just showed you that. That can also depend on vocal fold spec or on their structure. as I told you, we'll see in a second how that differs from speech to speech and from gender to gender. But in general, in bilabial lips, Trill's lips open and close 20 to 25 times a second. Mine were opening and closing 30 times a second, so I'm above average. In modal voicing, the global trill cycle recurs on average 120 times a second for men, so that's what I had approximately for myself, 220 times a second for women, and 300 and plus times a second for children. These are pretty reliable measures, although bear in mind that these are averages, right? But this is the number of times you are opening and closing your vocal folds in normal voicing. Okay, now another thing we have to pay attention to is that air rushes through vocal folds at 20 to 50 meters per second. We're expressing these in meters because the distance is very small and the volume is small. If you want to convert these into units we're more familiar with, the ones we use when driving a vehicle, for example, you can say that the air is moving with the speed of 72 and between 72 and 180 kilometers per hour. These are the units for that. Or if you're American, and I don't suggest you be at this point. I'm joking. Yeah, it's just because of miles per second or per hour, miles per hour in this case. So pretty fast, right? Very fast. Due to Bernoulli effect, the pressure between vocal folds when this occurs is very small, and the speed of glottal trill cycle depends on thickness of vocal folds, denseness, and length. So, as I said, this opening and closing cycle and the number, the period, and the frequency depend on the thickness, on the denseness, on the length of vocal folds. This means that basically it differs from person to person, but as I said, these are pretty reliable measurements for per gender, right, and per age group. Yeah, so we have an analogy here, and I think this is a good analogy between the vocal folds and string instruments. For example, with respect to denseness, you can think about a string instrument on a violin, a guitar, for example. If you tighten the string, then the tenseness will increase. So if you tighten it, right, the tenseness will increase. I don't know, if I tighten this paper, tenseness will increase. If I loose it, it will loosen up a little bit, just like a string. So when the tenseness increases, the string can produce higher sounds, such as E, right? If you loosen up a string a little bit, the string will vibrate slower, right? And as you know, the string will become slack, which means they will be producing a lower pitch, such as E instead of E, right? You can control the vocal folds in the same way. So you just ask any music teacher, and when you're doing the rehearsal, I don't know if you have done any rehearsals with your music teachers. I have, and I know that they were making us sing like lo, li, la, right, in different tonalities, so with different under different tones, by controlling our vocal folds. So you can produce li, low and high by tightening and loosening up your vocal folds. That's what you do basically. Yeah. So, and that has to do with tenseness. So this is how you would make your vocal folds tense. Right. In men, vocal folds are 70 to 23 millimeters long. In women, vocal folds are 12 to 17 millimeters long, which means that the shorter the vocal folds, and the thick they are, the faster they vibrate, right? Because they're smaller. For men, they vibrate slower because we have bigger vocal folds, and that's why we have low voices in comparison to maybe high voices. I'm just caricaturizing, yeah, here. Adult male vocal folds are 2 to 5 millimeters thick. Adult female vocal folds are slightly thinner, as what I said. Thicker, longer vocal folds vibrate more slowly. Think violin strings versus bass strings, for example. Violin strings are shorter, I don't know, this long, right? Maybe longer, but this long, and bass strings are long, right? Because of the bass. Bass is huge, and the bass is making this boom, 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 boom noise, and the violin can make different types of noises, but mostly higher noises, right? They will vibrate much faster than bass strings. And the same ways for women and men. Tenseness of vocal folds can be changed to alter the speed of glottal opening and closing, like a tuning a violin or guitar. If you ever done that, you know, those musicians that come before the show, and they tune their violins and guitars and string instruments. You've probably seen it in rehearsals. They do this basically. They just want their instrument to sound properly, to hit the right notes. Alright, so some terminology that we want to cover is the acoustic terminology or acoustic linguistic terminology. And we're slowly, as I said, entering into the basic acoustics. Frequency is the rate, so how often, right, at which vocal folds are opening and closing, measured in hertz. I've already explained that. You can go back to that part in the video. Period is the length of time between cycles. Frequency equals 1 per period, and period equals 1 per frequency. Yeah. I'll change this here and say frequency, and period, right? All right. Pitch is the perception of frequency. So how we perceive it, it's not actually the frequency of what's going on, but how we perceive it. When we perceive a lower frequency, when the frequency is lower, when we have a lower number of cycles per second, then we are making lower voices, right? We're talking lower voices. We're making lower sounds. When we are having higher number of cycles per second, we're making higher frequency, right? So that's how it should sound, without being foolish as I am. All right. Because these concern the larynx, we call them laryngeal settings, right? So we know of 2 basic laryngeal settings for any pulmonic aggressive sound. Vocal folds are adducted. Air from lungs makes vocal folds trill, so it makes them trill like this. And we make voice sounds, so vocal folds are vibrating, like an E or Z, right? Vocal folds are abducted, held apart. Air passes through glottis unobstructed, and we make voices sounds, such as S, right? All right, so we now know these 2 settings. How independent are speech sounds one from another? Stops can be voiced or voiceless, and there are 2 anatomically independent settings: place of articulation and voiced and voicelessness. So phonation and place of articulation can be independent. Yes, absolutely, they can. However, can they be aerodynamically independent of each other? So when you think about it, phonation is concerned with your glottis, and then you make a stop somewhere in your vocal tract, such as K or G, right? And whether you vibrate vocal folds or not, that's completely independent of that. But what about flow of air? is it influenced by these two properties? Do we change it? What do we do with it? And can it be independent for vocal folds or phonation and for other places of articulation? In other terms, is it easier to make a voiced or a voiceless stop? And we can think about these in those terms, because I'll show you why, right? Let me give you first cross-linguistic data, and you can think about what's easier to make. This is an old survey from 1976 from Ruren, who surveyed 706 languages. 75% had both voiced and voiceless stops. Of the remaining 25%, 24.5% had only voiceless, and 0.5 had only voice stops. So basically, I don't know, maybe one language out of the remaining had only voice stops. And I'll show you some data from UPSID or UPSID again. There are 322 voices bilabial stops, voiced bilabial stops, voiceless 402, voiced alveolar stops 137, voiceless 185, voiced velar stops 283, voiceless 438. Apparently, voice stops are hard. There are more voiceless stops in the UPSID or UPSID, and this also survey of languages shows you that voice stops are harder and therefore less common than voiceless stops. Why is that? Again, we have to wonder what's happening here. And I'll take you one step further. Are some voice stops harder than others? For English, the situation is clear. But the g, but the g, we have both, right? Both versions, voiced and voiceless. For Thai, we have but the k, but missing g. For Efik, we have p missing. Something is happening there, but g seems to be missing as well. Okay, so it looks like we are missing some stops there, and yeah, we have bada, right? And g again is missing, so that's important to add. Let me walk you through one step further. From Sherman, 1975, who surveyed the stop inventories of 87 languages, 2 languages were missing voiced bilabials, 21 languages were missing voiced dental alveolars, 40 languages were missing voiced velars, and voiced velars, which means that voiced velars are particularly hard. Remember the g, right? And why is that so? Why? You can think about it, but and many linguists or many phoneticians would say, oh, it's historical. And in history or previously, you actually had more voiced velars than you do today. But what happened? What happened actually is this. And we have aerodynamics again. So these are the lips. This is the mouth, pharynx, and glottis. This is a schematized version, right? And we need to think of this tract as volume, and how volume, like chamber, and how that relates to the place of articulation. So voicing occurs when air flows through the glottis, right? Airflow going through the glottis. Glottis closes and opens very fast, so air needs to flow, right? The air pressure below the glottis has to be higher than above, right? In order for the air to go up. That is crucial because the air will want to move from high to low areas of pressure. So let's say, yeah, I already said this. So let's say that I get the voicing started and I close off the lips. So I have the voicing like and I close off the lips, right? If I close the lips, this is an this is a sealed chamber of air. I get a sealed chamber of air. The air has nowhere to go, right? It's like sipping water into the bottle, or sipping water through here, and if I continue sipping, the water has nowhere to go, right? And eventually there will be no more space for it. So air is flowing through the glottis. The air above the glottis will have nowhere to go. And this is important. The pressure above is going to increase and the pressure below will decrease. And if that keeps happening, something dynamic is going to occur. That's why we call it aerodynamics. Something is happening, right? The difference between the two will decrease. And so air pressure below the glottis will drop, air pressure above the glottis will rise, the difference between the two will decrease. And if decreases to the point where there is no air pressure anymore, the voicing will stop, airflow will cease. And just logically thinking, if you keep voicing and the air has nowhere to go, the air pressure will level off, or it will be diminished to zero, and the voicing will stop. So you cannot keep it forever. Like if you start voicing, try making a b by first voicing it. I don't have anywhere to put air anymore, so the voicing stops, right? The pressure is equal, and I have to open my mouth, right? So you can't keep it forever. Voicing will stop for sure. Now, if the chamber is smaller here, the less volume there is above the glottis for air to move into, right? This is what happens to G, and this is again the example of G, right? But the voicing ceases very quickly. It's hard to keep the voicing going, and if the air has nowhere to go, it kind of kills itself off, right? It kills itself very, very quickly, more quickly than you would think for B or P or D. Oh, sorry, no, not P, but B or D, right? Bilabial and alveolar. Now, yeah, as I said, if you try to make a truly voiced B, you might end up making an implosive as well, because you will do your best to try to keep the airflow going, and you will lower your glottis. So you will lower your glottis in order to make space for air, as you do for implosives, right? You briefly expand the space above the glottis, which keeps the differential pressure. And to keep the voicing going on, you can keep the pressure differential by making a nasal. You can also say something like you can nasal. You can make a nasal for as long as you want, because the air has somewhere to escape. But for B or for any kind of stop, the voicing has to stop, or you are otherwise making an implosive, right? That can happen as well. So P above, or pressure above, will increase more rapidly as air flows through the glottis. Voicing will cease more quickly, and that's what happens with G. That's why G is not so prominent. More numbers. Let me give you some more numbers from Catford, who wrote Fundamental Problems in Phonetics in 1982. Lung volume is around this much capacity, centimeters per cube. During inhalation, exhalation, lung volume typically changes 500 to 1000 centimeters. Vocal tract volumes is equal to the space between glottis and oral closure, right? Glottis and oral closure, wherever it is. For bilabials, it's larger, right? And therefore, the amount is larger, the amount of volume of air. For alveolars, it's smaller, so the amount is smaller, and for velars, it's very small. And you can see, in each case, this is a small portion of air coming out when you make these sounds in comparison to lung volume. And this is why velars are even worse than bilabials and alveolars, and this is why they are often reduced. They often languages often don't have the voiced velar. The morals of the story are the following. Voice stops are hard because too much air gets pushed into the mouth behind the stop closure, right? That makes it impossible for there to be pressure drop above the glottis. Voiced velars are worse because the space above the glottis behind the stop closure is even smaller. This space gets filled up by pulmonic airflow even faster, and that's quite important. And that's what we talked about just a minute ago. Finally, independent. You can have articulation independent or articulatory gestures interact independently, but they have to interact aerodynamically. They have to share the same stream of air, and that's where the independence stops. That's where we get certain sounds in certain languages and not in other languages, and that's how we, in the end, produce trills, right? By aerodynamic flow. This is a good introduction into basic acoustics, which will be our next lesson. So until then, see you and have a great day, weekend, whatever you're having.